Hi, so what I'm going to do in this module is, we've talked about the Faulkner-Scan equation, right? So please look that up, okay? What I'm going to really talk about is that when we sort of solve that, right, for various values of alpha 1, beta, and so on and so forth, what kind of solutions do we get and what do those mean, right? So basically I'm going to just play around with this code and change the values and see what we get and how we're going to deal with that and so on and so forth, okay? So this is, I'm not going to the grind of this, we've talked about this previously, right, for the flat plate. So now this is the Faulkner-Scan equation, okay, and I have alpha 1 is 1, okay, and alpha 1 is 1. I don't know if I've written it here somewhere. So again, I will repeat myself. I will post this online. You can take it, but I think you can find it online also. It's not a problem. So you could do that as well, or you could just take this, no problem. Okay, so now so this is essentially the solution that we will get, and here I have this beta value of 0.6. Okay, so this here is the beta value, which is 0.6. Okay, so let me go ahead. So I'm doing this in Scilab, okay, which is similar to MATLAB, but like I've said before, the syntax is slightly different. I use that on my computer, so you can take this, just convert this code to any platform that you're comfortable doing it, and you should be able to get it to work, okay? So let's see, if I were to run this, what do I get? Okay, now so we get all these values. We get all these values. Let me look at this one, which is because this is of most interest to me, because this is basically the u by u infinity, like, right? If you see this, so this is u by u infinity, which is the f dash, isn't it? So I hope it is not too light, you can see that. So we get a curve like this. So eta is on the x-axis, and f dash or y2 or u by u infinity is on the perpendicular axis, and this is what it looks like. Now what I'm going to do here is save this. Okay, I'm going to save just this one. Okay, and what I'm going to do is change this beta around. Okay, plot several one of these and see what this kind of looks like, and how it changes and things like that. Okay, so let me sort of save this. So let's say I'm going to copy to clipboards, because this is just for my own understanding. And this is also to show you kind of stuff you do to understand things, or I mean, how do you interpret your code? Okay, pretty much how you do interpret your code. So this is the one, and what I'm going to do is write here. So this is basically my beta, right? So beta is 0.6. Okay, so beta is 0.6, so I'm going to write that there. Okay, so let that be there. So the beta is 0.6. Now let us do something here. So what I'm going to do is change this beta value. It is 0.6. Okay, so let me make that as 1, and let's see what happens. Okay, if I do that, so now I'm going to go and run this again. Okay, let me close that. So I'm just, like I said, I'm playing around with this and trying to show you what this looks like. So you should be able to place other values of alpha 1, or do other things with it. So, and I hope you do that. I'm just kind of showing you one of the ways you could have fun with this, really. Okay, so you can clearly see now this becomes, it's quite different from what we were getting last time. Already you can see this, already you can see this. So this here is for beta, and you can see this for beta 0.6. Okay, let me save this first, and then we're going to talk about the two. Okay, So let's say we're going to do that. Okay. So this is beta is equal to 1. Okay, so this here beta is equal to 1. Okay, so now easily you can see here that for beta 1, when eta is equal to 5, right, which is like really far off, it goes like really high. U by U infinity is like very, very high. Okay, so eta 0, so U by infinity is 0, and it's like nearly 0 almost everywhere. Okay, till about 4 from 5, it really shoots up. Okay, so there's some, and here basically it lies, it's a little positive for some time till about say 1.5 or so, but then it is like negative and it goes from 0 to minus 5. That's how it lies. It's like parabolic shape. Here it's pretty much constant, and there's not much change at all, except towards the as you go kind of a little away, so you see that it's really shooting up. It shoots up. Okay, so okay, fine. Now what about if I put this as 0? Okay, if I said this was 0, then what would we get? Okay, so let's do that. So this, okay, I'm going to keep that, and beta is 0. So what do you have to say about that? Do you recognize this in any way? Does this ring a bell? Beta 0 here? Does this ring a bell? Well, I hope you recognize that this is similar to, this is basically a flat plate solution, right? So we are doing the Faulkner-Scanlon equation, which also incorporates. So if beta is 0, and beta is 0, alpha 1 is 1, what does the Faulkner-Scanlon equation reduce to? Okay, so go and look that up. So this should give you interesting. So again, so here of course it is 0 to 1. Okay, it lies between 0 to 1. At 5, it's nearly 1. Okay, so U by U infinity. So what you can basically see that you at 5, which is kind of eta 5, so it's like U, or the U is almost equal to the free stream. Okay, it's almost equal to the free stream, and this is interesting that when you have beta is equal to 0.6, U seems to be in the opposite direction of U infinity because it is negative. Okay, and when beta is equal to 1, okay, so U really shoots up. So U is like 200 times faster than free stream. So that's interesting. So let's okay. So we seem to get we've got a 0. So we got beta 0, we got beta 1, okay, and so we got beta 0, we got beta 1 and beta 0.6. But I think that it is okay. Let's do one thing and make this very small, and I'm going to make this at 0.1. Okay, if I do 0.1, what do I get? I'm interested to know that how this exactly, why am I doing point? What is my thought process? Why do I want to do that? I want to do this because I want to check that how sensitive the equation is, right? The Faulkner-Scanlon equation is to these constants. I would like to know that. So okay, let's save that again. So here beta is equal to 0.1. Okay, so now if you see, okay, that's crazy, the beta 1. So beta 0, okay, so beta 0, when I went up to 5, eta is equal to 5, it's nearly 1, right, free stream. When beta is equal to 0.1, right, if I increase beta, then you can see the, I mean, at least till about say 3.5, the nature is not much different, okay. After that, it turns to curve down, right. It turns to curve down the velocity, but here, and it is obviously here it is the till about 3.5, there is not much difference between, the slopes seem to be also same between beta 0 and beta 0.1, right, but it's slowly sloping off towards the you know, farther end. Okay, let's see. So in that case, let's go ahead and change this to say 0.2 and see how is the change, right? There's not, the change is not too drastic from you know, 0 to 0.1. So let us see if this really becomes drastic or not. Okay. Okay, let's see. Okay, that seems to be quite large. Okay, that seems to be quite large. Now let us see. Okay. Point 0.2, right? This is 0.2. Okay. So this is 0.2. So now, if you see this, this is very interesting. So this is 0.1. Okay. So this is 0. Okay. This is 0.1. Okay, which is not that much. But when I go to 0.2, it sharps off. Okay, it is pretty sharp, and then what you can see, it's like, you know, it's not even it goes up to 0.5. That's like the highest. What I see from here, from what my understanding is from this plot here, is that till about say, you know, 2, actually eta is equal to 2, the free stream reaches about half. The u basically, it reaches about half the free stream, you know, not even fully, but around half the free stream velocity. Here it reaches at least around 7. Here it's for beta is equal to 0.1. If I look at this, till about 3, actually, till about 3, it reaches about 70% of, and not, I mean, like, yeah, 0.7 times, so 70% of the, say, the free stream, right? So it's 0.7 actually of the free stream. Beta is 0, as you can see that it's around, say, you know, yeah, 5 or even, you know, 3.5. Around 3.5 it reaches about, you know, the fully, the you know, almost 100% of the free stream. And this is crazy, of course, 1 is crazy. So since now I'm intrigued that this goes like really sharp, there was not much difference between you know, 0 and 0.1, but it's quite sharp when you go to 0.2. Since it's sensitive, I'll do this one more time. I'll do this 0.3 and see what we get, and then maybe we'll do a smaller, you know, stuff. Okay, so if I do that, okay. So, I mean, that's pretty sharp, right? So what happens here is that so beta is 0.3, right? It's 0.3. So that's interesting. So this is 0.1, okay, this is 0.3, this is 0.1, okay, and this of course is your 0. Okay, so I got a lot of these, so let me sort of arrange this a little bit. Okay, so we got that, so beta is that, beta is that. Okay, so I got a lot of these now, windows opened up, but it would be interesting. So this is 0.1. Let's see, didn't we do a 0.2? I thought we did, right? So let us see. Where can I? This is 0.2, probably no. Okay. Yeah, well, I saw that, I think. Well, you know, you can curse me for this. This is not the ideal way to do it. No, it's not. I'm just trying to explain that, you know, how you could have fun with your computer and stuff like that. Okay, so this is 0.2. Okay, this is 0.3. So let me just again, you know, do this. Let's do this like this. So we got that. Okay, we got that. We got that. We got this. Okay, so anyway, we can write it like this, beta 1, right? And this goes down really sharp, isn't it? So you've got that, then you've got this, okay, and you've got this. It's very sharp, and then you get beta 3, and so on and so forth, and so on and so forth. So we have all these things, and then of course we have, you know, 1, which is like really crazy. Okay, so what we see is that this was 0.2 and 0.3 now. So clearly here, so here also it's like totally positive, though here also it is positive. Okay, positive in the sense that free stream, the u is, you know, in the direction of the free stream. So here also it is positive. Now here for till about 2.5, like I said, it reached that and it came down, but it's still positive, right? But if the moment we go to beta is equal to 0.3, what we see is that beyond eta is equal to 1.5, u is actually negative. It's negative. So if it is negative, then, you know, we'll have to think about it. What's, you know, so it's basically that. So therefore, you know, beta is equal to 0.3. So we see that, you know, from 1.5. So and beta is equal to 0.6. Majority of this is, you know, negative. So let me play around a little more with this. Let me play around with this a little more. And what I'm going to do is, now that we know what, you know, so this is what you do to play around with the code, okay, and you know, do all of these things, enjoy yourself, and then, you know, finally that gives you a lot of insight, and, you know, you work on your stuff. So just keep doing stuff and see what you get. So now again, so what, let me do this. I've never gone above 1, okay, so I'll do that, and I'll also do a negative. Let's see what we get. Okay, what does this code do? So 1, say 1.1, okay. So if I do that, what do I get? If I do 1.1, what does it do? Whew. Wow, okay. So this is 1.1, which is not actually, you know, much different from this. If you look at this, it's almost the same. It's almost the same. What is different is that this goes up to, at eta is equal to 5, it is 250, and this is almost, it's actually, you know, more than double, because it's like 700, okay. So this is 1.1. So it like doubles just by, if I change it by 0.1. So if I do 0.2, then what do I get? Okay, this is like really crazy, okay. So it goes into the negative, what I can see. It goes into the negative, and it's like really, really negative. Okay, so I don't think this is even, you know, I don't think the computer can even solve this, right? So this is like, there's no much difference. If you go closer into this, probably we will, you know, see some stuff. I don't know if you can see something. No, it's actually pretty, it is. I mean, sometimes you can go in and then see that, but no, it's actually 0. It is 0, isn't it? Okay, so that's something. So what about if I were to make this negative? Does that give me a solution? Say 0.1. If I did negative 0.1, what would that be? Would that even run? Well, we seem to get something, okay. Wow, that's interesting, right? So if I do a minus 0.1, right, so I actually get, well, it's not much difference from the beta is equal to 0 case. So it seems like it may not be very sensitive, or is that so? I'm not sure. So it is slightly above, 1. It was around 0.95 or so for the beta is equal to 0 case, right? So this is it. Okay, let me go slightly further and say that this is minus 1. Okay. If I do that, then what happens? Wow, so that is interesting. Okay, so if I go to minus 1, it is kind of, so it's kind of behaving in that, tone. So we have some interesting curves if it is minus 1. So, but what I see is it's not, it's still positive. It's still positive. What if I do this as minus 5? Okay, if I do this minus 5, then what do I get? Okay, so that's interesting. So if I do minus 5, we tend to get a lot of undulations here. Okay, so we get this curve something like this. Okay, so but it is close to this 1. So the free stream velocity, is u is close to the free stream velocity. A little high sometimes, but say 1.6 times or 1.65 times or something. But it's close to it. It's not not something like 250 times or 600 times or something. So at least it's close to the free stream velocity. So making this negative is not too bad at all. So if I make that 10, then what happens? Okay, so this is basically the numerical nature, what this is going to do. So I get, yes, I was kind of expecting that. So we would get, some more, something like this, some more, undulations here. But what is interesting is this one is kind of remains the same. It's just that it's shifted a little bit to the left. That's all. Okay, we get one more. I'm going to give this a try. I'm enjoying myself. Let's do this a little bit more. Let's see what we get. Okay, so if I do that, right, so we get one more. Right, we get one more. But this actually remains, like that, and we keep adding to it. Do you see that? So the velocity is quite interesting. What I'm finding interesting is that it's following like a, sinusoidal curve or something. Seems to, have that. So if I were to make this 100, what does that mean? If I were to do that, that's interesting, right? It's not following any that's really interesting. Wow, that's interesting, because this is very, very interesting, because this is a kind of velocity profile. This is if you were to take, an airfoil, right? And if you had, this is almost like, it's becoming highly unsteady kind of a motion, if you see, right? It is changing so frequently. So, so if you take, if you're pitching airfoil, or a pitching wing, or you see even a very small birds, they flutter like that. So the velocity profile comes out to be like this. And it's what I see is kind of dying down to the more you increase the beta negative, it's concentrating here, it's doing more, but then it's nice and sinusoidal. This is very, very interesting. So this gives you ideas as to how to, use this equation and how this is going to help you do that. Yeah, so we keep repeating the same thing. So we get the same thing, which is very, very interesting. Okay, so it becomes more and more, you know, yeah, it's periodic. It seems to be a periodic, but that amplitude is decreasing as we go, you know, as eta is increasing. Amplitude is largest, okay, it goes from 0 actually, goes from 0 and goes back and forth and back and forth. And as the amplitude is decreasing, and it's, you know, very nice and sinusoidal, and it goes up there, okay. So if I make this really, really large, then what happens? One more time. Okay, so you can basically, what I'm trying to say here is use this code and, you know, do things to it. Yeah, I think this is like, is probably not even able to draw it. Okay, so I don't think it's even able to draw it. So it didn't work. Okay, so for whatever reason it was not able to draw it. If I were to do, yeah, it can still draw it. Okay. It might have been a numerical stuff. Wow, this is very interesting, isn't it? So if you do something like negative 500, so there's not much, it dies down pretty quickly. That's the whole thing, right? You have the unsteadiness, but then it dies down pretty quickly. Okay, there's not much. It's kind of, you can see that is a free stream, right? So 1, when u by u infinity is 1, it means it's free stream. So it dies down and it becomes a free stream very quickly. That's all. Okay, so if I were to go 600, then what happens? Okay, I mean, we'll get the same thing. So right, so it dies down even quicker. That's what I can see. Okay, it moves. Okay, it moves. So therefore, if I had this, okay, so right, so here you would have it, and so if you have sort of a large value of negative beta, then the unsteadiness will die out very quickly, you know, eta will die out quickly. If not, it will take a while, you know, to die out. So that's what I can see from this code. So basically, you know, the point is that now I've inspected just the beta. Okay, I've inspected just the f double dash function, which is u by u infinity, and there are the other things which I didn't look at. So you know, you could actually do that and play around with that and see what it is like, and make some head or tail out of it. To try and understand what's going on and make inferences out of it, and also try and understand that numerically what this is doing to the code, right? So that is that was my whole purpose of doing this, that, you know, you write a code and then you play around with it and see, you know, what it is doing. So the way I'd like to put it, you know, initially when you're developing the code, you know, you are the boss. You know, the code will do what you expect it to do. But once the code is debugged and it's up and running, you know, it's actually a person on its own. So it has a mind, and then it is able to tell you things which you slowly pick up. Okay, so that, I mean, this is the code, and this is again the fourth Runge-Kutta that, as I've explained to you before. So this is similar to, this is exactly the same what we've been doing earlier. So well, I will of course post this, and you should be able to you know, see this and get so you should be able to, you know, get a copy of this code, and on your own also you could actually you know, look at the internet and get that. But essentially the whole thing is that you should be able to, you know, we are plotting, all the plot that I did is basically for eta, and I think it'll start making a lot of sense when you plot these things, when you plot the velocity profile in the x and y coordinate system, and then that's when it really starts making you know, interesting. So but this thing was very interesting, that if the beta is negative, right, initially you don't realize, and the beta in the negative side is less sensitive. which is what I saw, but in the positive side it's like really, really sensitive. So you make a small change and it was like changing quite a lot, right? And the beta is equal to 1 didn't even make sense to me. Okay, but here it is interesting that you know what kind of problem you're wanting to solve, and you know the velocity profiles is something that you should be able to read. Okay, so I think I will stop here, and I'll take up something next time. And what I will do in the assignments is basically not ask you to write a code, which is fine. You know, you don't have to write a code and all of that, but be able to interpret what's in it. You know, whatever we are getting. When we get a plot out of it, what's important is how you interpret it. I think that's the major part of research. Okay, so that would be interesting. Okay, so what I would expect you to do is go ahead and spend some time and figure out what each plot means in terms of, say, x and y coordinate system, you know, away from the plate and so on and so forth. Okay, so I will stop here and see you another time. Thanks.